Our focus in this course when we talk about surfaces is to be able to visualize them in your mind without necessarily requiring the artistic skill to sketch them on paper. Part of the skill of imagining the graphs is going to be using some features of the graph that are outlined here and to apply that to various scenarios. What we're going to go through is a sequence of examples where we give you a function and show you the graph, and we try to build up that association so you could get a sense for how these graphs are, why they're shaped the way they are when we look at them as surfaces. A few things that we might look at, I'm not going to go through all of these, this is a reference sheet, but some that we're going to use immediately are the idea of looking whether z is positive or negative. This is something you do with one variable functions, of course, but it plays an important role in getting a basic sense of the shape of a graph in two variables as well. The other things that we might want to look at are looking at along the axes. So if we have a graph and we set x equal to 0, well, that's this plane going front to back here. So we can say, well, what happens to this graph? Sorry, x equals 0 is the plane going the other way. If x is coming out of the board, then x equals 0 is this plane here. And that's a nice one for sketching because that's the one that we would typically draw as a regular one variable function. So if we can study what happens when x equals 0 and get a cross-section of the graph, then we're well on our way to figuring out at least something about the entire shape of the graph. What we might also do is sub in other values besides 0 into x and y just to see what happens. Other questions, of course, what happens at large values as x gets bigger and y gets bigger? What happens to the function? There are important features that we're going to see again in the upcoming examples, such as if we have something that's linear in x and y, you're going to get a plane. Here's an interesting one. If you always see x and y appearing together as x squared plus y squared, then what's happening there is you could basically replace that with the distance to the origin. And so if a function depends on that, it depends only on the distance to the origin, then that means everything at the same distance will have the same height, and so you'll get something that looks circularly symmetric, and we'll see how that plays out in terms of our graphs. And our last example will feature this last thing. I think we'll have forgotten it by then, so we'll come back to it when it's relevant. All right. So here's a simple intro example of a real multivariate function. F of xy equals x squared plus y squared. And this particular graph shows the structure that we just talked about the x squared plus y squared. So that's our cue, that there's circular symmetry. And what we can see here is that, yeah, as we go around circles here, we're always at the same height. It's cut off at the edges here in a square way, so it's a little lost, but we'll see how we can build it up maybe in a different perspective and get a hand sketch that's at least reasonable. A couple of other features we might note is that z is always positive. We take a look at the x squared and y squared. No matter what values I pick for x and y, we always get a positive value. What else could we learn? Well, let's go for the cross sections. At x equals 0, z gets simplified. It becomes 0 plus y squared. So if we were just to take a slice through our graph in x and y only, or sorry, in y and z only, so if we use this x equals 0 cross section, which again is this plane in y and z only, well, what are we going to get? We're going to get a simple parabola. You can't get too tied down to the variables you're using. It's enough to say we have y as an input and z as an output. So we would get a parabolic shape. And the classic parabola, simply the y equals x squared shaped parabola. With that, and if we add the circular symmetry in, well, guess what? That gives us an instant view on the shape of the entire graph, the whole entire surface. Let me tweak this up a bit here. There we go. We're going to get a bowl shape. We're going to get this parabolic arc spun around because at every location, say I move out in x and y, Well, I'm going to get a height, and that height's going to depend on how far we are away from the origin. And this particular shape is often referred to as the parabolic bowl shape, or just the parabolic bowl, because it has that parabolic building block, and it's simply spun around, so it has a nice bowl symmetric shape around the origin. Here's another example which has that circular motif, but it's in a more complicated function, including an exponential here. But the first thing to recognize is that circular symmetry. Then, again, as soon as you see that symmetry, it's really tempting to ask what happens at x equals 0. Because if you do that, then you get the shape in one cross section. And what happens there? We'd have e to the minus y squared. And once again, we can draw that in two stages. We can talk about the y versus z graph. And if we recognize this shape, this is our classic bell curve. E to the negative something squared has the shape of our normal bell curve, like so. If we recognize that, add in the circular symmetry, and guess what? Then all of a sudden we have this shape spun out in 3 dimensions. So we have a bell-shaped hill. And that's what we see here with the vertical scale a little emphasized, but we can see that it's circularly symmetric. It has a peak at the center, just like the bell curve, and then it fades away. It's also worth noting what happens at the extreme values as x and y go towards infinity, plus or negative infinity. What happens? We get e to the negative large values, and that, of course, converges towards 0. So the z values that we get, the heights that we get as we move outwards in y or outwards in x, are going to fade away towards a height of 0. And that's not shown here in the scale, but we can predict that from the shape of the formula here. All right, what about another circular symmetry? We love these because at least they simplify life. Trust me, we'll see more complicated and more exotic functions later on. This is a good one, good introduction to graphing though, so it's nice to start off simple and work up towards those more challenging examples. All right, let's take a look at this square root of x squared plus y squared. So it's not, first off, it's not z equals x squared plus y squared, which was the parabolic bowl. It's close to that. Somehow it's similar, but it's not equal to that because of this square root, because of that radical sign. Now, given that, what can we do? Well, we certainly do see the circular symmetry. That is going to be present because every x and y appears always with the x squared plus y squared form. So what can we do? Well, let's do that same example or same approach that we used earlier. Let's let x equal 0. And then if we call our function values here our z's or our heights, we're going to have the square root of y squared. 0 plus y squared. Well, that's interesting. Now, the temptation, of course, is to say, oh, well, that's just y. But it's not quite that simple because if y is positive, well, sure, we get a positive y here when we square root it. But what if y was negative? What if we had like -1 squared? We'd end up with -1 squared square rooted. Well, that's the square root of +1, and remember, every time we have a square root, the reason we put negatives out front is to make it explicit. The square root by itself is always the positive square root. So we'd end up with +1 here. So what just happened? When we had -y values coming in, we ended up with the same value but positive on the way back out. And so we'd end up with the absolute value of y being our function or height, so long as x equals 0. Now again, let's leverage that circular symmetry. We just said in these two directions, y, z, let's bring this to the negative side as well. We would have a graph that looks like the absolute value function. Oops. Let's try to draw this a little more straight. There we go. There we go. So this graph is the graph of z equals the absolute value of y. So positive values are just y equals z, and the negative values get flipped up. But we also have the circular symmetry. If we add that in, guess what happens? Well, we add some depth to this axis. All of a sudden we have an x-axis, and everything that we had in this plane gets spun around. Let me try to connect that a bit better. And so this shape, which would keep going on forever, is a downwards, a cone with a peak at the bottom, or an upwards open cone. So this function here, square root of x squared plus y squared, is not going to be a parabolic bowl which had that curve to it. This is going to be made entirely of straight segments forming a cone shape because of the circular symmetry and because of the simple shape that we get when we let x equal 0 and limit ourselves to that. All right, moving right along. Here's another example. This one's a little less interesting in some sense. It goes back to one of the earlier rules I mentioned that we had not seen yet. But this is linear in x and y. Notice there's no powers. Just constant multipliers. And that means that the shape of the surface is a plane. Oops. There we are. The shape of the surface is a plane. Now here it's really hard to tell where the x and y axes are. Again, with planes with straight objects, it's surprisingly difficult to visualize them as a 3D sketch or a 3D perspective drawing in 2D. We actually do much better with curved surfaces because there's transitions, there's changes of slope that our eyes are really good at detecting and understanding. With purely flat planes, we don't have any depth perception that we can apply here, and so it becomes much less intuitive. But from the simple form, we know that it's going to look like a plane. Last but not least in our sequence of examples for now, we have an example with no y values in the formula. Now what does that mean? Well, it means regardless of the y value, the z value remains constant. Or better yet, for all y values, the z value is constant, or z changes only when x changes. What we see here, and again, remember we do these axes in a little different way than we would in one variable. Positive x is going out this way, so the sine function actually would look like this. Then along the y direction, well, as long as I don't change y, I don't change my height. So in fact, we get a ribbon effect when one variable is missing. I guess it's not really missing, it's just not used in the calculations. But in this case here, we have the sine graph that's marching towards us, and it would be shown as a ribbon marching towards us when we include that third dimension, the y direction. So that takes a little bit of practice to see, and just think of calculating values. You can always go back to a table of values and say, well, what's sine of x equals 0? Well, that's 0. What's sine of pi over 2? What's going to be sine of pi over 2 is 1. What happens if I used x was pi over 2 but y was something? Well, it would have no effect on the calculation, so we get exactly the same height. So if you can get into that mentality of what would happen if I picked a certain x and y coordinate, positive, negative, whatever, plug it into this formula, what height do I get? Then you can work through very mechanically why we get this ribbon formation if one of the values is missing, one of the variables, input variables is missing. Of course, if we made it sine y, the sine curve would be going off towards the right, and it'd be a ribbon moving off towards the right. So that's a gentle introduction through example of some of the surfaces we can expect to be dealing with when we're talking about functions of two variables. As I mentioned as well, we're going to be looking at alternate ways to represent these graphs simply because these can't be drawn very easily by hand, and there are better tools using computers to do it for us. But we'll see more of that as we move through the unit.